Hello and welcome back to Counting Rocks and Introduction to Combinatorics at CSU. Today we're going to be talking about two additional proof techniques that we haven't seen before, proof by contradiction and the pigeonhole principle. So let's start with proof by contradiction, which is a very classic proof technique that comes up everywhere in mathematics. A contradiction is a statement of the form P is true and also P is false. We agree in mathematics, just like we agreed on the principle of mathematical induction, that we can take it as an axiom that contradictions cannot be true. You can't have a statement that is true and false at the same time. So an example of a contradiction would be if you prove x is less than 5 and x is bigger than or equal to 5, whatever x is, that's impossible. You can't have a statement and its negation at the same time. So here's how we do proof by contradiction. We assume a statement Q is true. Say we want to prove Q is false. We assume it's true. If we can use that to prove a contradiction, then we realize that our assumption must have been false. Because if we can use an assumption to prove something that's clearly incorrect, then our assumption must not have been correct, and so we can conclude that Q is false. So here's a classic example of proof by contradiction. How do we prove that the square root of 5 is irrational? To prove something by contradiction, you assume that the opposite of your statement is true. You assume, instead of that it's irrational, you assume that it's rational. And then we try to use that to prove some contradiction and see what's wrong with it. So if it's rational, let's see what goes wrong. Rational means that it's a fraction. So square root of 5 then is a over b for some integers a and b that share no common prime factor. We're going to write it in reduced fraction form, so if they had a common prime factor, we can simplify the fraction. This is just saying we're writing it as a simplified fraction. Then squaring both sides of this and rearranging, putting the b squared on the other side, we get 5b squared equals a squared. But what this means is the left-hand side is divisible by 5, and so is the right-hand side, so a squared is divisible by 5. But since 5 is a prime, the only way a squared can be divisible by it is if a is divisible by it too. So now we know a is divisible by 5. Okay, but then the right-hand side is the square of something divisible by 5, which is divisible by 25. And so that means this part has 25 dividing it, 2 5s, and so there must be an extra 5 over here on the left somewhere coming from the b. So b has to be divisible by 5 too. But then a and b do have to share a common prime factor, 5, but that contradicts our assumption that we wrote it as a simplified fraction and they don't have any common prime factors. So how could they both be divisible by 5 if they can't both be divisible by 5? We have both that something is true and that it's not true at the same time. That's a contradiction. So we can go all the way back up to our assumption and realize that that's where we went wrong. Our assumption was wrong, that square root of 5 was rational, so therefore it's irrational. Here's another proof technique that comes up in combinatorics that you can actually prove using contradiction. It's called the Pigeonhole Principle, but we also think of it as a proof technique itself. It says that if you put m pigeons into n holes, and m is bigger than n, if there's more pigeons than holes, then some hole has to contain at least 2 pigeons. Here's these 3 pigeons, we're trying to fit them into these 2 boxes, and there's just not enough room. Some hole is going to have 2 pigeons in it. They're going to have to share. So, proof by contradiction. Why is the pigeonhole principle true? Well, let's assume that it's not true. Assume that m is bigger than n, but every hole can have at most 1 pigeon. Then there's at most n pigeons, because there's n holes, so m, the number of pigeons, is less than or equal to m. That contradicts our assumption that m is bigger than n. So we get a contradiction, and actually our assumption was wrong. Some hole has to have at least 2 pigeons. Now let's use the pigeonhole principle itself to prove things in combinatorics. Here's an example of pigeonholing numbers. Given 6 integers, show that some 2 have a difference that is divisible by 5. So this is involving modular arithmetic and going back to divisibility. And this should make you think of the pigeonhole principle when you see a problem like this, or a proof that you want to do that's of the form, show that something exists. If you want to show existence, sometimes the pigeonhole principle is good because the statement is some 2 pigeons are in the same hole. So existence of a pair is a good sign that we might want to use the pigeonhole principle. The trick is to figure out what are the pigeons and what are the holes to be able to apply the principle. In this case, the pigeons are just the 6 numbers. The holes are the 5 remainders that you can get mod 5. So when you divide things by 5, what are the possible remainders? 0, 1, 2, 3, or 4. So since there's 6 numbers and only 5 holes, some 2 numbers have to have the same remainder. One of these remainders contains 2 of the pigeons. So some two of these numbers, no matter what our 6 numbers are, have the same remainder mod 5, and so their difference is divisible by 5, because those remainders will subtract to give you 0. Let's look at a slightly more complicated example where you can still use the pigeonhole principle, but the pigeons are a little more tricky to find. Show that among 5 integers a, b, c, d, and e, any 5 integers, some consecutive sum of them is divisible by 5. What do I mean by a consecutive sum? I mean consecutive alphabetically, like a plus b or b plus c plus d, but not like b plus e. That skips some numbers. It's not consecutive. So let's take our pigeons to be the following 6 numbers: 0, a plus b, a plus b plus c, a plus b plus c plus d, and a plus b plus c plus d plus e. So I'm taking all the initial sums starting from 0, just moving from left to right. The wholes again can be the remainders mod 5. So there's 6 pigeons and only 5 wholes, so some 2 pigeons have the same remainder. The difference is always a consecutive sum. Even if 0 is one of your pigeons in the same whole as like a plus b plus c, then a plus b plus c minus 0 is still a consecutive sum. It's a plus b plus c. Or if we happen to have the 2 pigeons that are in the same whole being a plus b plus c plus d and a plus b, well, their difference then is divisible by 5 because they have the same remainder, and their difference is a consecutive sum. If we knock off the a plus b part from the initial part of that sum, then we get still a consecutive sum, c plus d, remaining. And that's going to be divisible by 5. Here's a geometric example. Given 5 points inside a 2 by 2 square, show some pair of them have to be at most square root of 2 apart. So if it's a 2 by 2 square, first of all, the distance from the center to an endpoint is square root of 2. So you might want to argue that, well, if we try to put the points as far away as we possibly can, 4 points on the corners and then 1 in the middle, well then there's still a distance of square root of 2. So you can't possibly make them further than square root of 2 apart. And that's an intuitive argument, but it's not really rigorous. How do we know we can't sort of shuffle around these points a little bit in some weird pentagon way so that actually the distances are all greater than square root of 2? Well, here's where the pigeonhole principle comes in. Let's make the pigeons be our 5 points, but let's make our holes be the 4 quadrants of this divided up 2 by 2 square, where I divided it up into 1 by 1 corners. And now each 1 by 1 corner has every pair of points within it being no more than square root of 2 apart. And by the pigeonhole principle, some pair of points must be in the same box. These 2 points in this case are at most square root of 2 apart because square root of 2 is the diameter of the whole square, so you can't possibly be further away than that. So the pigeonhole principle makes rigorous something that was just intuitive before, and that's what's very important about it for combinatorial problems and mathematics problems in general. There's one more generalized version of the pigeonhole principle where if you have a lot of pigeons and only a few holes, you can actually have a lower bound on how many pigeons must be in the same hole. If m pigeons are put in n holes and m is at least k times n plus 1, then some hole contains at least k plus 1 pigeons. As an example, among 17 positive integers, show some 4 of them have all the same remainder as each other when divided by 5. So again, the pigeons are 17 integers and the holes are 5 remainders, but 17 is bigger than or equal to 3 times 5 plus 1, which is 16. So some whole, some remainder, has to contain at least 3 plus 1, or 4, of these integers. And you can think of this intuitively by, if we had only 15 numbers, then we could have 3 in each remainder, and we wouldn't be forced to have 4. But as soon as we have 16 or 17, we're forced to have some remainder having 4 of the pigeons. So now you try, if 9 points are placed in a 2 by 2 unit square, prove that some 3 of them are all within distance square root of 2 of each other. And that's all for today, and I'll see you next time.